You may have also noticed right above r was an r squared. This is called the coefficient of determination or the proportion of variation, just two phrases for the same thing. It really is the r value squared, so you could find it yourself as well, but they do both appear on that screen. And what that tells you, it's actually an interesting piece of information because it tells you the proportion of the variation in y that is explained by the relationship between x and y. So what I mean by that is, let's say you found this for the relationship between the weight of a car and the highway mileage. That would actually tell you the percentage effect that the weight has on the highway mileage. So highway mileage can be affected by lots of different things. This would be the percentage of that was actually from the weight. So let's go ahead and calculate that, and then we can talk about that interpretation a little bit more. So we created this scatter diagram. Let's go ahead and with that data that should still be in your calculator, we'll go find the correlation coefficient and the coefficient of determination. So the information should still be in stat edit. Go to stat tests, scroll down, find the LinRegTTest, calculate, and when you scroll down you find that the R value for this sample is negative 0.818, 3 decimal places. We're not talking significant digits, just 3 decimal places. And so that's a fairly strong correlation, 0.8. It's negative 0.8 because it was a negative correlation. And then the R squared is 0.669. So looking here on this slide, that is a percentage actually. So we can change that to 66.9%. The R value is not a percentage, but the R squared is. And so that literally means that the highway mileage on these cars was all different. 66.9% of those differences are because of the car's weight. So that means 33.1% is from other factors. So highway mileage is affected mostly by the weights of the cars, 66.9%, but 33.1% of that is actually other factors. And then, as I mentioned, negative 0.818 seems to be a fairly strong correlation, but how do we know if that correlation is actually strong enough to be meaningful and useful? There's actually no concrete cutoff point. Like, I can't just say 0.8 is a good correlation and anything less than that is not, because it actually depends on the sample size, and significance levels come in as well, just like they did in the last chapter. So if I have a very large sample, I'm going to trust it a little bit more, and I'm going to be willing to accept a smaller correlation coefficient. But if I have a small sample, then I'm probably going to want to see that correlation coefficient be a little stronger to be sure, because with small samples you just can't be as sure about things. And so what we're trying to do is use information from a sample to determine if the population is also going to have a correlation. So what we end up doing to relate those two is a hypothesis test, just like we did in the last chapter. So we're going to figure out, is this R value from this sample strong enough to say that the population probably does have a correlation? And so we'll do very similar process to the last chapter, find a p-value and go from there. So remember the point estimate thing from the last chapter. The statistic from the sample is your point estimate for the population. So in this case, R is our point estimate for rho. And so we'll set up a hypothesis test, put the information into the calculator, test our claim using a p-value. So since we're trying to make a claim about rho for the population, just a quick reminder, the closer to 1 the better, so 0 would mean no correlation, and that goes for both R values and rho values, since they're both correlations, just one for the sample, one for the population. We're going to run through the same 5 steps from hypothesis testing in the last chapter. We're going to set up our hypotheses, we're going to say what test we're doing, find a p-value, and then make these decisions about rejecting or failing to reject the null and supporting or failing to support the alternative, and then coming up with a nice sentence interpretation. Our hypotheses on these will actually always look the same, which is kind of nice. your null hypothesis, remember, always has to be equal to something. And so our null hypothesis is going to be that the coefficient equals 0. Now remember, equaling 0 means that there's no correlation at all. So our null hypothesis is that there's no correlation. And then our alternative, we don't really care whether it's a positive or a negative, we just want to know if there's a correlation at all, so we'll say not equal to 0 to take care of both directions. So this will pretty much be what your hypotheses look like every time. You can make that alternative a greater than or a less than, but we're not going to worry about that, just to simplify things. So in this class that will always be a not equal. And then, as I mentioned, that LinRegTTest screen that we use to find the R is also the one that we're going to use to do the hypothesis test. So you'll go to that screen to enter the information to find the p-value. So you'll go to Stat Tests, you'll scroll all the way down, find the LinRegTTest. Make sure that the X list and the Y list are correct. And then you can actually go to the line with the not equal, less than, greater than. Make sure the not equal is chosen, because that's always going to be our alternative. That's supposed to be a little row symbol there. There's a beta in front of it as well. Don't worry about that. You can actually test beta as well, but that's not something that we're going to worry about. And then you'll go down to calculate. Don't put anything under regression equation. Just go straight down to calculate. And then that's going to pull up a screen with, again, lots of different information. The P's pretty close to the top there, and so in this case it's 0.00382. 3 significant digits on your p-values, remember. So let's back up then and look at how to do that hypothesis test from start to finish. So at the 0.05 level of significance, we're going to set up the hypothesis test and determine whether there's enough evidence for a correlation between the weight of a car and its highway mileage per gallon. So first step is to set up your hypotheses. Our null is going to be that there's no correlation at all between the two, so rho equals 0. Our alternative is that there is a correlation one direction or another, so we'll just say not equal to 0. You go to your stat tests, get your LinRegTTest like we just looked at, p-value 0.00382, and then we had a significance level of 0.05. This is definitely smaller than that. Remember that that p-value is talking about the null, so that is a small enough chance that we can reject that null hypothesis, which means we're going to support the other one, which was the alternative. And this is the case, we don't have the word fail in here anywhere, so there is sufficient evidence in this case to support a linear correlation, that was the alternative, between weight and highway miles per gallon in all cars. So we've taken the correlation that we saw in the sample and said, yes, that is strong enough to support a correlation in the whole population. And we can look at that R value to determine whether that was a positive or a negative relationship. Remember that that R value was negative 0.818, so that is a negative correlation. Here's another example if you want to pause and get these two lists in your stat edit. Just some sort of employee test score versus performance rating. And we're going to test at the 0.05 level of significance for a linear correlation. So we set up our hypotheses. Notice that they look exactly the same. No correlation for the null, some sort of correlation either direction for the alternative. We go do the LinRegTTest. In this case, the p-value comes out to 0.192. Well, that is bigger than 0.05. So in this case, that is not small enough to rule out the null. We fail to reject the null. That means we fail to support the other one, the alternative. We've got the word fail in here, so this is a case where there's not sufficient evidence to support the alternative, which was that there was a correlation. So there's not sufficient evidence to support a linear correlation between test scores and performance ratings for all employees.